In this video, we're going to discuss the idea of area function and the second fundamental theorem of calculus. So let's start by looking at a simple function. I'll label it as little f of x that has a graph like this. It consists of semicircular arcs and then a little line segment over here. And this is a nice function because we can compute lots of different integrals just knowing some basic geometry. So for example, if I want to compute the integral from 0 to 4, that's the same as that shaded area. So I would take a circle of radius 2. It would have an area of 2, it would have an area of pi times 2 squared, which is 4 pi, but then I only want half of that, so the integral would be 2 pi. So the integral from 0 to 4 is equal to 2 pi. Let's say we wanted to compute the integral or signed area between 0 and 8. Well, we would take this area, which we've just computed, 2 pi, and we would have to add to that the area of this triangle. This triangle has a base of 4 and a height of 6. And if I take 1/2 base times the height, I get 12. So the integral from 0 to 8, which is that signed area, is equal to 2 pi plus 12, which I'll leave as is. What about the integral from x equals 0 to x equals 0? Well, that's pretty stupid because there's no area to start with. But we'll just make note of that, so we just get 0. The integral from 0 to 4. Now the order of integration is unnatural because I'm going from a larger to a smaller endpoint. So let's switch back to the natural order of integration where we go from a smaller to a larger by putting a minus sign out in front. So now I need to compute the integral from -4 to 0 of f of x, and that's just that signed area up there. Well, we already know that this area is 2 pi, so this signed area, because the graph is below, is minus 2 pi. But then we have the original minus sign out in front, so we get 2 pi. Then finally the integral from 0 to -2 of f of x. Again, it's the unnatural order of integration, so we switch to the natural order of integration by introducing a negative sign there. So now we have the integral from -2 to 0 of f, and between -2 and 0 we're going to have that signed area, which is minus pi, but then we have the minus sign out in front, so we get pi. Now, what do all of these examples have in common? Well, they're all definite integrals, obviously, and the lower endpoint is just 0 for each of these. I just happened to choose that the lower endpoint was 0 for all of these. So depending upon what the upper endpoint is, I get a number back. Upper endpoint is 8, I get this. Upper endpoint is 4. I'm sorry, -4, I get 2 pi, so on and so forth. So I can make a table of values, which I'll do right here. So I'll put the upper endpoint right there, and I'll put it right there as well. I'll just put a little box. If what we put in the box was 8, the value of the integral was 2 pi plus 12. If what we put in the box was 4, we got 2 pi, and so on and so forth. So for each value, each number that I substituted in there, I got back a single number over here. That means that what I have here is a table for a function. Now typically when we work with functions, it's very common to think of the variable x as the input, so I'd maybe put an x here. Now the problem with that is that when I look at what's happening over here, I would have the integral from x equals 0 up to x equals x. Well, what does it mean to say x equals x up here? That really doesn't make sense. Usually we're used to going from, 0 to 5 or something like that, but to go from x equals 0 to x equals x wouldn't make sense. And so what we do to get around that difficulty is everywhere we see an x in the original integral, we replace that x with a t. It still counts the same amount of area. So what I've done, now I have, instead of the box here, I have an x, that's my variable. And now what I've done over here is I've replaced that box with an X, and I'm simply going to use a different letter of different variable of integration here. I'm going to use T. If you'd like to use S or alpha or W, any number, any letter you want except X, because we're reserving it for the upper endpoint. Now we can make a table of values, X, and then the value of this over here. So think about this as our Y values, and these are our X values. So this is a very different type of function. We give it a name. We call this function where we put a variable X up here and we replace the variable of integration to T or something else. We call this an area function, or an area accumulation function. It records how much area there is, signed area, between the graph of F, the horizontal axis, 0, and X. I chose the lower endpoint to be 0. That was my choice. You could use 2 or 3, anything you want, so long as it's in the domain of the function. So A of X measures the signed area between the graph of F, 0, X, and the horizontal axis. Let's look at another example here. So my area function is going to be defined in terms of the integral. Again, I'm going to use from 0 up to X. So we're going to start counting the area from 0 and stop at X. Now if I want the area between 0 and 0, A of 0, that means I'll have a lower endpoint of 0 and an upper endpoint of 0. So that just gives me 0. A of 1 would be the amount of area accumulated by the function little f from 0 to 1. That's going to be the area of this square plus the area of this triangle. And if you compute those two quantities and add them together, you get 2. A of 2, that would be the area of that triangle plus the area of that square plus the area of that triangle as well over here, and A of 2 would be 7/2. You may want to stop the video and just add the area of that triangle, that square, and that triangle together. A of 4 would be how much area we accumulated up to 2, which we know to be 7/2, and then we would have to subtract this signed area. This is a circle of radius, a semicircle of radius 1. So the area of a circle of radius 1 is pi. We take half of that because it's a half circle, but then the graph is below, so that contributes minus pi over 2. So our area function A of 4 is the amount of signed area if we start at 0 and go out to 4, and it's 7/2 minus pi over 2. If I want A of 6, it would be the amount of area I accumulated between 0 and 4, and then we add to that how much area is accumulated between 4 and 6. So we take that 7/2 minus pi over 2. I've got a circle of radius 2. So the area of a circle of radius 2 would be 4 pi. I want a quarter of that, so that's just going to add another pi on. So I'll have my 7/2 minus pi over 2, that's the amount of area I accumulated up to 4, plus the amount of area we've accumulated up to 6, which is pi, so we get 7/2 minus pi over 2 plus pi, or 7/2 plus pi over 2. A of 8 would be how much we accumulated up to 6, plus we'd have to add another pi over 2 on again. We'd have to add another pi on, we'd have to add another pi on. So I'd have this add another pi on, that pi is that area right there, so I'd have 7/2 plus 3 pi over 2, that's a 3. A of 9 would be how much area we accumulated out to 8, which we already know is 7/2 plus 3 pi over 2, and then we'd have to account for this area. This is a triangle of area 1/2, but the graph is below, so that's a negative 1/2, so we would get 7/2 plus 3 pi over 2 minus 1/2. In other words, 3 plus 3 pi over 2. So we have evaluated the area function, the area accumulation function at various values of x. Now here are some observations. First, if f is positive on an interval, then the area function is increasing there. And here's why that is. We start accumulating the area, we start counting the area at the origin. As I move my pen from left to right, we are adding on more positive signed area because this graph is above the axis. Adding on more signed area, more signed area, more positive signed area. But then when we hit this point at 2, we're starting to accumulate negative signed area. So we go from more positive signed area to losing some signed area because the graph is below. So the graph of little f is above, below, above, and below. So my area function is increasing. Then we start to lose area, so decreasing. Then we start to add area back on, so increasing and decreasing. So again, this function is above, below, which corresponds to the area function being increasing, decreasing, increasing, and decreasing. Okay, so my area function is increasing if x is between 0 and 2, and from 4 up to 8, my area function is decreasing if x is between 2 and 4, and if x is greater than or equal to 8. Now, let's make another observation. I'm going to take a look at a little snapshot of the function. I'm going to draw a little horizontal band right here. So this is a portion of the function. It doesn't matter which portion I'm looking at. And of course, because the graph is above here, this is my little f, this is a positive amount of area, positive signed area. Now I'm going to go over here and I'm going to draw a band of the same width. Now notice how the width is the same, but the height is larger because this function is increasing. So I've got a greater area for this band than I do for that band. So in other words, let's say I draw a band of common width and I move it from left to right. Because this function is increasing, I'm starting to accrue or accumulate area more rapidly. So as I go from here to here, I'm accumulating area more rapidly, but then I start to accrue or accumulate area less rapidly because the function little f is going down over there. If little f is increasing, then the area function is increasing more rapidly. We could also say that the area function is increasing at an increasing rate. Well, what does it mean for a function to be increasing at an increasing rate? Well, if the function is increasing at an increasing rate, it has this sort of shape here. In other words, if little f is increasing on an interval, a of x is concave up there. If a function is decreasing, little f is decreasing, the area function would be concave down there. I'm sorry, if little f is decreasing, a is concave down. So let's summarize it in this table. If the area function is increasing, little f is positive. If the area function is decreasing, little f is negative. The area function is concave up precisely when little f is increasing. It is concave down precisely when little f is decreasing. This is just a function derivative relation. This is suggesting that the derivative of the area function is little f. Or in other words, little f is the derivative of the area function. Or in other words, the area function is an antiderivative of little f. And this is what we call the second fundamental theorem of calculus. Succinctly, exactly. Suppose little f is continuous on the interval from a to b. Then we can construct an area function which is an antiderivative of little f. All we have to do is take our function little f and replace x with t, and then we integrate from t equals a to t equals x, f of t dt. Again, you don't want to use x in here because we're reserving it for that upper endpoint. You've got to use something else, t or s or something other than x. I'm using a t here, which is quite common. And I should also point out that the value of a is arbitrary so long as f is continuous there. So I was using 0 as my lower endpoint, but you could use a 5 or something like that, and you'd still get an antiderivative. And that makes sense because functions generally have infinitely many antiderivatives. So this is really a theoretical result. We don't use it to evaluate integrals, but it really is a theoretical result insofar as it tells us that even the nastiest functions have antiderivatives. So here's a function. Little f is e to the x squared, sine of the quantity cube root of x to the third plus 1. What would an antiderivative of this function be? Well, I don't know. I mean, it's not like anything we've encountered before. It's not in our table of integrals, so to speak. We've got e to the x squared. We've got all this stuff right here. It's a mess. We could spend hours trying to compute the antiderivative, a nice formula. But the second fundamental theorem of calculus says that you can cook one up by taking this formula, replacing x with a t, and simply integrate from t equals 0 up to t equals x. And again, I chose 0. I could choose something else if I wanted to. So the fundamental theorem of calculus is really more of a theoretical result. We don't use it to evaluate integrals. Here are some problems for you to try. I have this function, little f, 1, 2, so on and so forth. You can assume that there's a maximum at -1 and at 1/2 and a minimum at 1.5. And we'll define the area function capital F to be the integral from 0 to x of little f of t dt. So it's the area accumulation function associated with this graph. On one interval is capital F increasing. Where is it decreasing? Where is it concave up? Where is it concave down? That's problem A. Problem B asks you to determine an antiderivative of the function f of x equals e to the x squared. And a hint, it's not just e to the x squared. So see what you can do on this prior to class.